Hey everybody, Adam Savage here. I am in Austin, Texas on the grounds of Icon. And behind me, you know how much I've been into 3D printing in the last few years. Behind me is the largest 3D printer you or I have ever seen. Evan, how are you?
Good, how are you?
Tell me about this beautiful machine.
Well, we're here at Printland in Austin, Texas, looking at Icon's Vulcan 2.5 series. It's our Block 4 fourth generation printer, printing some test specimens for a project we're about to go do.
But its main job is it prints houses.
It does.
Okay, talk to me about printing 3D printed houses.
Sure, so picture the FDM printer you have at home that's extruding plastic. More or less the same thing, just a different material and a totally different scale. So
you guys are running concrete building materials through your printer.
Exactly, concrete cementitious materials, we call it Carbon X, and that's the material that we use to build our homes additively, one layer at a time from the ground up.
And this isn't a prototype. You guys have been printing, how many houses has Icon printed over the past few years?
Gosh, we're north of 200 permitted structures that are permanent.
Amazing. Permanent structures. People are living in houses you've printed with this printer.
Absolutely. We're printing at scale. You can buy a house right now and go and live in it and just really enjoy it.
And so this area we're in is called Printland. Is this where you test and develop and improve and come up with future versions of these machines?
Exactly. So back when we just had the one headquarters building, 10,000 square feet, we learned pretty quick we need to test how we fly.
Yeah.
And so we came out here, and this is sort of our playground for research and development, but it's also for print readiness, and it's to test new kind of emerging technologies, and we don't get to take any shortcuts out here. It's the real deal, often off-grid, just like it would be on a job site.
Oh man. So I was watching it go, and I don't know about you, but like I actually like sitting watching my 3D printers at home go. I find the process fascinating. I find this even more sort of mesmerizing, watching the concrete slowly come out of this thing layer after layer.
Yeah, it's knowing what actually goes into making this all work. It's just an absolute symphony of a bunch of motors and pumps and sensors and all sorts of things just to take that kind of two-part epoxy that we wet it down and we pump it 200 plus feet and it comes out the nozzle just right.
Amazing.
And we have to do that all day, every day, 24/7, 365.
Okay, so let's say I've got a building site and you guys bring your gantry. Once the printer starts printing, how long before there's the basic structure of a house?
Well, there's actually a really interesting phenomenon that I didn't know about until I lived it, and most people wouldn't, where you go from something that feels like lines on the ground that you're printing all of a sudden to the realization that you're inside a house. And I don't know exactly when that happens. It probably changes by the floor plan, but that's a really magical moment. So you'll get a little bit of that feeling today on the slab, but yeah, we just go about a layer at a time depending on the house. Could be 30, could be 40 minutes per layer as we raise that house layer by layer. And we just print continuously till we're at the top.
I heard tell that you have been able to print a house in as little as 24 hours?
With a reasonable square footage, we can stack beads pretty quickly.
Amazing. Is this the form you guys are devoted to, or are you developing new ways of printing houses?
So this Vulcan is our workhorse.
Right.
It's our printer. We've been relying on it for a few years now out in the field. We're printing at scale with it. But we are looking at a new form factor called Phoenix. It's going to really change the way we print.
Will I get to see some of Phoenix while I'm here?
Absolutely.
Amazing. Can we get up closer and see this thing going?
Yeah, sure.
Awesome. Hi, Sydney.
Hi, Adam.
Nice to meet you.
Nice to meet you too.
Okay, I'm looking up close here and I'm noticing some textures I haven't seen yet. Is that also is experimentation and iteration part of the task here?
Absolutely, absolutely. So one of the things we test is like our advanced wall geometries, or what we call them. So behind us we have the basket weave.
The basket weave looks good.
The basket weave. So this is on an upcoming project, our Mueller project. So we're testing out this print path with CIR, which is our inline continuous stainless steel reinforcement.
Oh, wow.
So that's what's happening behind us today.
This is so much more like a 3D printer than I even realized. So you can put a metamaterial into it as you're laying it down.
Yes, exactly. So this is what is inside of the bead. So that is being extruded out of the nozzle. You can't really tell, which is kind of the point, right?
Yeah.
But if you listen, you can hear it cut every once in a while towards the end of an item. And that's kind of a cue, like, oh, it cut, it's in there.
Oh, that's so neat. And when this is done running through its paces, do you guys come in and peel these up and do materials testing on them?
These will demo, and like we kind of try to recycle the concrete
I
we
see.
demo here. But we also do material testing. Like on another printer, we have a new material, like on 252 over in the other corner,
Yeah.
we're testing out a new material that's going to be more resistant to cracking. So our materials team is over there working on that right now.
All right, so here it is. And so this is laying down as it's printing there. It's laying this inside.
Correct. Did you hear that? Did you just hear it cut?
I did.
So it's about to end that item. So that's a cut up in the system. And so the rest of it is coming down and extruding as it ends that item.
And that sound means that it's cut the cable.
It cut the cable.
Fascinating. I think when people think 3D printing houses, they're not quite realizing that it's literally exactly like a filament printer.
Yeah, it is quite similar, right? And isn't it quite satisfying how uniform it is?
It is so satisfying. And each time to the next layer is carefully timed to allow it to set the right amount, am I right?
Correct.
Okay.
So I mean, in a typical, like if we're printing, for example, like obviously we're at Printland, so it's kind of like a Frankenstein Mod Podge of walls.
Right.
So this isn't like a typical curing time, but for
Sure.
example, when we're printing full houses, like a lift time can be 30 minutes to an hour.
I
And especially
see.
in the Texas heat, that's plenty of time for your concrete to cure and you to print on top of it.
Gotcha. All right, Evan, we've seen the orthogonality of Vulcan, and now this is Phoenix?
This is the Phoenix engineering prototype, yes.
Okay.
Version 1.
This, I'm sorry, I'm just kind of getting over my shock. This actually works.
This
at the end
actually
of this
works.
arm, you're able to get the precision that you get out of Vulcan with this.
Yes, we were surprised too. The story goes essentially that it's really challenging to drive to work on a gantry while you see concrete pumps pumping foundations, and just wishing you could print with something that was shaped that way.
That was that
It
fast.
just makes so much sense from a
Right.
positioning and setup. But the challenge, of course, is how unstable it is as it's moving. And of course, all the challenges of the kinematic solution, making sure that you can actually move all of these large beams and linkages to the point you need them, not just one time, but continuously along a path.
Now, is this a Stewart platform I see at the end?
That is absolutely a Stewart
It
platform.
usually belongs at the other end of a machine.
Sure.
Tell me how this functions.
Sure. So they're used a lot on boats,
Yeah.
but essentially you have 6 extension actuators.
Right.
If you move them all just right, you can actually move this bottom platform in full 6 degrees of freedom.
X, Y, and
X, Y,
Z
Z,
space.
roll, pitch, and yaw.
Amazing.
To some extent.
Right.
And so because this system is limited in its excursion in those axes, we've also added, it's sort of a Stewart platform plus plus. It's got an extra roll and a pitch here. So that's what allows us to take this top section and level it to gravity with an accelerometer. So we level it, and then we get a nice flat plane at the top, and then we keep this as lightweight as possible, and this is just our nozzle down at the bottom.
And keeping this lightweight means that this can adjust to the grosser movements that are happening farther back on the machine.
Absolutely, and unfortunately we're not running it right now.
Right.
But you can set a beverage right here and just shake this top part of the crane, and it'll just hold it perfectly still.
Wow.
So that's what the Stewart platform gets us on this system.
There must be a maximum like wind threshold and other environmental conditions that this is going to operate under, but within that envelope, it achieves the same precision as the Vulcan.
Sure, and we simulated quite a bit before we actually had this piece of hardware. So this is a long lead time item that we bought, and we sort of took control of it with a computer, but before we did any of that, we built it all out in a simulation. So a full physics simulation where we can simulate wind, we can simulate a bird landing on it if we cared to. And then we actually use that motion or error in the motion to design the actual dynamics of this system. So we made sure that all the normal perturbations and speed and position and all those, we were capable of soaking these things up in this system.
So just to be clear, the reason you want to keep this light is because if it's heavy, it's going to have more inertia and it's going to be harder to correct for. So your whole goal is to have all of the weight be concentrated as far back as you can. Is that right?
Absolutely.
Amazing.
And there's even a strange trade there where if this becomes too stiff, the natural frequency of it goes too high, and we can't actually have the bandwidth to get this to move as quickly as we need to compensate it. So it's kind of a fine balance there, and that's why we lean heavily on simulation for all of this work. When we got this thing loaded up and started talking with its internal computer, we were 3 days of calibration before we were doing accurate Cartesian motion. So
Gotcha,
that was
gotcha.
all done in simulation, full loop closure, hardware in the loop, as much as we possibly can, and that's just to keep our velocity up. We're trying to go and get this out to the field.
Right. The goal is that it goes as fast as it can. That every hour matters.
Exactly, and it's so much easier to run design analysis cycles ahead of hardware. Hardware cycles are slower.
Right.
And so we want to get it as close to right as possible.
Now, from what I understand, this is a proof of concept, but it's not the final design for Phoenix.
Absolutely.
What are the improvements? What is going to change about the head of Phoenix?
Well, so this actually, again, is not our chosen form factor. There's a bunch of very strange nuances and things like easements and setbacks. So the delta between what this system is and what we actually are going to field with our Phoenix system is, I wouldn't say it's majorly substantial from most people looking out or looking from the outside in, but there are things like keep out zones and reach angles. So when we're trying to get to 2 stories tall, our boom system would hit a 2-story tall sort of rectilinear type house,
Right.
And it'd be hitting its elbow up against the house next door. So we just simply can't handle those types of constraints.
So there are ways in which even the smallness of this head is too large for some of the things you guys want to achieve.
Certainly. And we have to fold it up and be able to drive it and be able to fit it in a shipping container for international shipping.
Right.
We have to get it on an envelope of a truck to get it down the road. And so the packing factor, it just isn't really there for this form factor of robotics.
All right, so this is a 3D print of Phoenix 2.0. We've been talking a lot about what's going on here, and I can see the narrow head. But are there also improvements you've made in this on the whole arm going down to the base?
So everything's different between this and the actual engineering unit.
And you guys so this is basically a whole piece of earth moving equipment you're designing and building from scratch.
It's bespoke.
Amazing.
Yes, it is a robot.
Tell me about its unique
It is a very
features.
large scale robot.
Oh my God.
So as you mentioned, the more narrow, tighter tool head that gets us up against walls. It helps us with wall continuity if we do need to move in the middle of a print and be right up tight with another wall. So it lets us get in there like a little needle.
Yeah.
Now this is not little. We'll see in a minute.
Yeah.
But one of the key features here that we did was this redundant link here. Technically, from a kinematics perspective, it doesn't need this link.
Okay.
But we ran a substantial amount, billions of simulations of different kinematics and link lengths. So we basically Monte Carlo'd the entire space with certain constraints, such as the keep out zone here.
Right.
And it's very critical what these outriggers are, because we have here in Central Texas, at least in a lot of America, we have a 10-foot easement or 5 feet on each side. And so we've got a 10-foot gap right here that we've got to set this robot down in, and it has to reach all the way and not tip over with a substantial factor of safety, of course. Right, and so this does a few things. It raises this first link up so that we can build up to a 2nd story and not interfere. But you're also, when you need to come close over here, you're not hitting your neighbor's roof if the house already exists.
Because this isn't having to back up, but also it's a bunch of weight that allows you to extend farther out this way too.
So no counterweight here. We're essentially using the weight of the tracks as well as the outriggers to really just catch right up on that edge of where we need to reach, with a factor of safety, of course.
That is so fascinating. And then this whole thing can pack up. And how small can you get this? Can you drive this on a highway?
Unfortunately, this isn't bendable, but yes, you can turn this. It all folds up. Again, the packing factor here is critical to be able to fold that in without having to take it off in a secondary step. And then this thing actually can just lift itself up, drives the trailer underneath, and sets itself down.
Oh my God.
And then you're going to stick out a little bit here, but it'll fit on a standard 18-wheeler trailer. And then what's really awesome about it is with these track systems, they're basically bulldozer tracks.
Yeah.
You can lift up, walk it out, or drive it out from in between 2 homes. And if you're doing multiple homes on a home site, you can move it with just an operator. No commercial driver's license, no trailer and truck. You can just drive it around down the road.
Oh my God, so this must cut down the setup and tear down factor of the machine by a massive amount.
Substantially, probably a factor of 4 is about what we're shooting for. Also, it can sit on a grade and self-level. It's just a great form factor.
That's
but you have to stabilize it.
Right.
As you can see.
I'm just this is making me nervous. It's incredible. I'd love to take a look at the prototype.
Let's do it.
Oh, Hello, Jonathan.
Hey, great to see you.
Great to see you. So I've just been looking at the Stewart platform, and it's gone now. What is this? Tell me about what this is.
It is gone. And the Stewart platform did work fantastically for us, but in an end product, it's not exactly what we needed.
You wanted a smaller form factor to be able to print closer.
That's exactly right. So essentially, the Stewart platform has a big size to it. You can't really play with that very much without losing a lot of the range. And so we had to basically build something ourselves for our application. So what this is, we call it the fine positioner.
Yeah.
But it's still 6-off correction, but in the direction that we want.
6 degrees of freedom.
6 degrees of freedom. Yeah.
So this gives the same amount of freedom as what I was just looking at in a fraction of the form.
That's right, fraction of the form. Also, in certain areas, it's actually even larger range than the Stewart platform.
Wow.
So we actually have a yaw axis at the bottom here that can turn the nozzle. And we've got 2 axes at the top that acts like a gimbal, like a standard gimbal for a camera. And then a telescoping axis, which is very different from the Stewart platform.
And how does the telescoping axis work? Is it a ball screw or is it hydraulic?
It's a belt drive on the back side
wow.
here. So we've got servo belt drive. Yeah, yeah.
Amazing.
Very
And that
good for
gives you
high speed.
enough fidelity.
Yes, yes. So for all of these axes, we actually have a second encoder to make sure we're exactly where we want to
Gotcha.
be.
You're
That output
really
encoder.
monitoring position.
That's right.
That's the
right.
most critical.
That's it.
Before we get into the more details about
Yeah,
this,
yeah.
I want to talk about this rig because this rig tells me, it tells me a story, and it tells me a story that you guys are willing and able to knock out stuff very quickly to see if something works. And I
Yes.
get that it's a very iterative process here. Is that correct?
Yes, that's totally right. You can tell a lot of unpainted metal.
Yeah. No,
Yeah.
this is getting the job done to see if operation works.
That's it. So we've got the fab shop in the back. I think you met Scott.
Yeah. Water cutter or laser cutter?
Yeah, laser cutter. We've got
TIG welder.
routers. Exactly. So we do a lot of stuff in-house for prototyping.
Yeah.
And then we'll go and find the best supplier for long term. But we knock this stuff out really quick so we can iterate.
That's amazing.
You know, we're on like second version of a lot of these components. Down here, we're on the 4th or 5th just for this test rig. And then the whole test rig itself, we probably changed the design twice just to do it faster. But it's not just concrete that actually flows out of here.
There's metamaterials. You guys are adding stuff to the concrete.
Yes.
Okay, talk to me about that.
Yes.
Because I've seen the 3D printers where you
Yeah.
can add carbon fiber or other things within the 3D print.
Definitely.
Oh no!
So we have aircraft cable that actually gets inlaid with every single bead.
So you're eliminating rebar
That's
as a
right.
building material within concrete and replacing it.
That's right. Well, so this is fluid until we need it to solidify.
Right.
And this is on a spool until we need it in the right spot. And so we're trying to get as close to raw materials as you can
Right.
until the last instant. And then it serves its purpose for us.
This is crazy.
But this has allowed us to have the material properties more consistent throughout.
Oh,
When you're
interesting.
trying to place larger rebar, you've kind of got a lot of strength in one area and then, 12, 16 inches, another piece of rebar.
Right.
This spreads out the load and spreads out the strength. So you get the whole material being like, you said metamaterial, basically acting like a composite,
Wow.
right? Composite panel.
Yeah. And this prevents, I'm assuming it prevents cracking over time
Yes.
from thermal expansion.
It's very useful for shrinkage cracking also. So in the moment, the setting of the material, as it evaporates, as the water evaporates,
yeah.
it wants to shrink. This doesn't shrink, and so it keeps it in place.
That's awesome.
Yeah.
That's a wonderful added bonus.
If you're curious how it gets in there,
Yeah.
So-
this is the nozzle.
Yeah, let me
Oh, this
swap.
is your hot end.
this is clearly a used nozzle.
Yes.
Yeah.
Wow.
Yeah.
Okay, so the concrete pours through these two, three supported gates here.
That's right.
And there's a tube in the middle, and that's where the cable comes out.
That's right.
So there's something that pushes the cable.
Yes. Yes. So inside the googly-eyed magic white box,
So, are some spinning wheels.
some spinning wheels,
Gotcha.
but also some cutters. And so this even has a little bit of flex so that with the flow, it's aligning itself with the center of the bead.
Oh,
a lot
man.
of iteration. This is also 3D printed.
I thought this felt like
Yeah.
nylon.
Yes. Yes.
So you can, and is this a production nozzle?
Yeah.
You guys 3D print your,
Yes.
and I see the threads here, you just screw that
That's
in.
right.
Oh my gosh.
That's right.
So that means you can iterate design changes massively fast.
Yes. Yes. We've been as fast as every day a new iteration.
Wow.
Yeah.
Okay, I'm curious about if there are other things you're thinking about embedding in electrics, fiber optics, other stuff that you might put in that increases the functionality.
Lots of opportunities. We're always playing, always trying new things. Low voltage electricity
Right.
you could inlay. Like PoE kind of
Sensor,
level
potentially,
sensors.
right?
Yeah.
Oh man.
Heating elements in the wall.
So
That could actually heat up your inner wall.
So talk to me about where we are in the design process of this. Have you solved all the mechanical problems, or are you still working on some key things?
Still working on things,
Yep.
Assemblability, design for reliability. With Vulcan, it's all internally managed and run, so
Right.
we have a lot of support staff. We can just move to it. This has to be good for third-party use, and so reliability is basically amongst the top 1 or 2 sort of.
And this is reliability in the field, which is outdoors under environmental conditions, which are horrifying.
With
for
material that
equipment.
turns into a rock.
Oh, jeez. That wherever it gets on,
Yes.
it doesn't ever leave.
Yes.
That's people just don't realize how awful being outdoors is for equipment.
Yeah, if you think about all these specialties that we need to have in engineering at Icon,
Right.
it's across material science, it's across software, mechanical engineering, electrical, it's incredible.
So the final design look
Yeah.
of this may end up being, I would imagine, quite different than this in terms of how it's constructed.
There's a lot of wire management and stuff to
right.
improve, a lot of shielding that we're going to put on
Yeah.
for environmental. But in terms of the form factor, like the axes, gimbals at the top, telescoping,
Yeah.
3 axes at the bottom, we're pretty much there, and we're hitting functional. And then we've got the end of this year to get it optimized for use.
So the next step after this rig is bolting it onto the big arm and
then
seeing
printing.
how it performs?
Yeah,
Oh, man.
yeah,
I'm curious, within the world of 3D printers,
yeah.
if some of your software development is benefiting from the sort of leaps and bounds that 3D printers have undergone over the past few years.
It's interesting. I think there's probably more to come in the future, but we have found some of the limits of G-code. Yeah.
Amazing.
Yeah, and so sometimes you just have to do what's required.
That is really cool. Pushing right up against the limit.
Yeah.
Absolutely beautiful to watch it go.
Yeah.
What is it? Is there a bearing surface sliders on the inside of that housing?
Yeah, so this is running on 2 linear rails.
Ah, gotcha.
Right here.
Oh, okay, gotcha.
Yeah.
I see.
And then on the far side is the belt drive. Yeah.
Amazing. Jonathan, this is so thrilling. And this is the rig that makes me feel like I feel at home with this rig. I understand it.
Oh, you're always welcome, man.
Oh, dude, thank you so much. Really
Appreciate it.
appreciate it. All right, Jason, tell me what this is.
So we call this the House of Phoenix. And so when we developed the new architecture of our printers, so our first generation construction printers were this gantry style.
Right.
The gantry was great because it's very easy and straightforward to control, and precision is like really important when you're thinking about people's homes and
Obviously.
residences and 30-year mortgages and things like that.
Yeah.
But the gantry is difficult in the sense that it's logistically complicated to move and set up, and it sort of restricts how big and sort of varied the different things that you build are. And so
the gantry prints houses really fast, but the setup and takedown is laborious.
you got it. It can add like on the order of $10+ per square foot when you sort of average it out over the. So it's quite meaningful.
Okay, so this is the new technology. This is the Phoenix.
Yeah. So the sort of giant robot arm form factor. This is the first thing it ever printed, right? We sort of wanted to develop a print that would really put it through its paces and tell us what was working, what was not working.
So you
it's
printed
almost,
in, what do you call this, an Antelope Canyon or something?
Yeah, like it's like that Antelope Canyon. You're not the first person to make that observation that it has that sort of same effect on a person when you sort of walk into it. It sort of gets you all of a sudden, right? But yeah, so this is almost 30 feet tall. It's about 100 feet long. It literally is the first thing that our Phoenix prototype ever printed. And we didn't even know if we would be able to complete it.
Right.
But the success of this is what really gave us the conviction to continue to pursue that line of development. And so
And
that's what we're doing.
the Phoenix printer was able just to park. Was it able to park in a single spot to do this?
This all happened in a single setup. First, like we had done a few like test beads like on the ground, like
Right,
2 to 3
right.
layers. And then we moved out here and like just press send.
So you guys are, I really appreciate what I'm seeing is a sort of commitment to experimentation at the biggest scale you can try.
That's actually correct. And part of, you might say, like the reason that Icon exists, of course we want housing and construction to be faster and more affordable, but also like, you've heard people use the phrase like cookie cutter housing developments.
Right.
That sort of obedient repetition of the way that we build and the architectural styles that we use is somehow soul crushing. It's sort of, and part of the cool stuff about, one of the reasons that 3D printing is so compelling is not only that it could be faster and cheaper, but also that because your architecture is digital and the building material you're using is fluid when you lay it down, you have a tremendous amount of design freedom. So not only cost savings, but the sort of things that look very expensive from an architectural standpoint are very much on the table with 3D printing. And so imagine the world when things like this are faster and cheaper than boxes.
No, I know. I really love this. What I find surprising is the low-hanging fruit would be to just use your technology for structure and clad it and hide it.
Yeah, you almost could do that with the prototype.
And so you guys made the decision to actually make the manufacturing process visible and part of the aesthetic. So then I would imagine moving from the gantry to Phoenix, there's a lot of work to maintain the look that you want.
Yeah, there is. We have, because of course we do have affordability in mind on everything that we do, and of course the most affordable thing to do is if you can let the beads stand with no further finishing or treatment. That is the most affordable thing. So you can cover it up if you want, but we always want to have the option to revert to an unfinished bead, so that we keep the maximum affordability on the table.
I also love seeing 3D printing artifacts on a building size object that are the same as what I have in my desktop
100%. So there's, part of the using this for a test print, and in fact, the fact that we've left it standing here for so long is because you can do a kind of forensics on the building, right? When you see what we would call errors that are sort of random, that tells us usually that there's a materials control issue. When the error occurs in the same spot, top to bottom, that tells you something's happening mechanically that's creating some sort of deviation. And so it allows us to do a kind of forensics and improve the new printer itself.
So you must look at these layers and see like, oh, that fat layer means the mix is a little this way.
That's right. It definitely tells a story about where the printer's at, what it's capable of doing at this moment. And it sort of helps us focus on certain kinds of mostly mechanical sort of configurations of the machine, like when it bends a certain way at a certain speed at a certain angle, an error will appear, and so that's where we can sort of focus our efforts on stabilizing and making more consistent the deposition. But the material delivery system we have given equal, if not more, attention to, and in fact, what we're doing when we print is changing the material formulation in real time based on temperature, humidity, pressure, and irradiance, because 90 and cloudy is different than 90 and sunny, and so
the fluid's going to behave differently. It's going to set differently.
Yeah, and right now, actually, I think we're probably around 75 degrees right now, and this afternoon here in Austin, it will be well over 95 degrees, and material behaves very different in those temperatures, and so we have to be able to adjust on the fly because, of course, speed and corollarily cost matter to us. So we need to be able to turn the machine on and print come whatever weather brings.
I'm curious, when you printed this, did you also design it to push the envelope of engineering of this, to watch what happens when you do things that might be at the edge of its ability?
Yeah, this was very much meant to be sort of a test piece in that
regard.
Like,
so not just a showpiece of what you can do. You want to see what's possible.
Literally when we started, we didn't know if we would finish. So there was a little bit of like, let's see when it breaks and what breaks. And the fact that we got, like, I would have given you less than 10% chance that we made it all the way to the top.
You guys really love a challenge.
When we started. But yeah, if you look, there's no straight lines in this building, not vertically or horizontally are there any straight lines. And things are very dynamically changing. The angles of repose are changing as we go up, and they're sort of meeting each other at funny angles. And so it was just to see in our first prototype what the technology was capable of, where its problems were, and what its limits were. And then from a technical standpoint, maybe the important thing that this begins to hint at is, for the most of our existence, we've just 3D printed wall systems. This starts to hint at 3D printing the entire envelope of a building, the foundation, the wall system, and ultimately even roof enclosures. And now you really are attacking about half the cost of a building much more quickly and with much more beautiful forms. And it really starts to say, like, a lot of the magic that's possible with robotic construction is still in front of us.
Incredible.